So chapters 4, 5, and 6 all deal with quadratic functions. This video should be a quick refresher. It is by no means all of the topics you need to know, but it's just a way to get back into the topic because it has been a while since we've reviewed them. Chapters 4 talks about how to recognize a function through the equation, the table of values, or the graph. It talks about the three forms of quadratic equations, how to graph from each form, and determining the equation algebraically. Then in chapter 5, we looked at changing forms. So we expanded and we factored to go back and forth from standard and factored forms. And then in chapter 6, we completed square to change to vertex form. We found the roots by factoring or by using the quadratic formula. And we looked at solving problems, word questions to do with parabolas. So we're going to quickly go over those, and hopefully this will kind of jog your memory so that you can start looking at questions from chapters 4, 5, and 6 to practice for your exam. A quadratic equation is a second degree equation. So when we're looking at how to recognize that it's a quadratic equation compared to a linear or another equation, it's got an x squared in it, or it has x times x. So when we're looking at a quadratic equation, we're going to look for the exponent of 2 on the x, or for brackets and x is being multiplied. That tells you it's a parabola. We'll look at the forms of equations in a moment. Table of values. So when you're looking at a table of values, I'll draw a quick one right here. We are recognizing a quadratic function by calculating its finite differences. So first and second differences will tell us if the table of values is quadratic, linear, or neither. So quick example, -4 all the way up to 0. And we'll put in y values of 0, -1, 0, 3, and 8. If you're given those values, you could also be given just the x values and an equation to calculate the y values, but in this case I gave you both. If we're looking at these values and we're trying to figure out if this table of values represents a linear function, we would be calculating the first differences. So the change from 0 to -1, it goes down by 1. -1 to 0 goes up by 1. 0 to 3 goes up by 3. 3 to 8 goes up by 5. If these values were all the same, if the first differences were all the same number, like 1 the whole time, it would represent a linear function. In this case, they are not, so we're going to go ahead and calculate the second differences. The second differences are the change in first differences. So from -1 to 1, it goes up by 2 units. From 1 to 3, it goes up by 2. From 3 to 5, it also goes up by 2. When you see the second differences are all equal and that the x values are changing by the same number each time, so they're equally spaced out, because if these numbers were random, this wouldn't mean anything. If those are equally spaced and if the second differences are equal, that tells you it's a quadratic function. The graph of a quadratic function is a parabola. So I'm just going to import a quick graph into here. This is the graph of a parabola, and we're going to use it to identify important features or properties of the graph. So the most important part of this graph is the vertex. The vertex is the very, very bottom of the curve where it changes direction. When we name a vertex, we're going to use the coordinates of that point. So because in this graph your vertex is over 1 to the right and down 4 units, our x coordinate is 1, our y coordinate is -4, and we're going to write those in the brackets. 1, -4. The vertex I call the most important point because it helps us to determine two other properties of this graph. The x coordinate of the vertex, that +1, gives us the equation for the axis of symmetry. So I'm going to draw in an axis of symmetry here. It is a vertical line that goes right through the vertex. Oops, my line doesn't want to go there. Let's move it over. It goes right through the vertex, and it shows us the middle of the parabola where the left and the right sides are symmetrical. So this is my axis of symmetry right there. My axis of symmetry has an equation. When I label it, I'm going to label it with the equation x equals, oh, my arrow won't move here. That's okay. X equals the x coordinate of the vertex. So in this case, x equals +1 is the equation for my axis of symmetry. I use this number right here to make that equation. The other half of the vertex, the -4, is important because it tells us our optimal value. The optimal value just means the maximum or the minimum. In this case, it happens to be a minimum value because my parabola opens up, so my minimum is equal to -4. If my graph were opening down, this would have a maximum value at the vertex. It's just the y-coordinate of the vertex. Some other important points in the graph, we have two roots in this case, -1 and +3. The three words for those 2 points are x-intercepts, roots, and zeros. And when we're naming those, we don't give coordinates, we just say the numbers. So -1 and +3. Please don't put a comma. So those are important features as well. And then lastly, we have the y-intercept, which is kind of hiding here. It's our -3 where the parabola crosses the y-axis. So y-intercept equals -3. So that's how to recognize the graph of a parabola. Now, when we're looking at the graph, we have to know how to explain that this is just not any curve, this is a parabolic curve. So the first important point is the symmetry. It has an axis of symmetry. So when we look at our parabola, it's symmetrical, and our curve follows something called the step pattern. When you start at the vertex and you go over 1 unit, you go up 1 unit. Then you go over 1 and up 3. Then you go over 1 and up 5. Those patterns are the step patterns. And when you look at a graph, you can see if it's a parabola by the symmetry of the graph and also by the fact that the points followed show you the step pattern. So it goes over 1, up 1, over 1, up 3, over 1, up 5. This is your step pattern. And if somebody asks you to explain the step pattern, you need to know that it always goes over by 1 and it goes up or down by 1, 3, 5 times the A value. Sorry, my calibration of the screen's off a little bit here. I hope you can read that. So the step pattern shows you the A value or the stretch or compression of the parabola by going over 1 always and up or down by 1, 3, 5 times whatever that factor would be. So we've talked about how to recognize equation, table of values, and graph. We've talked about a little bit about the forms of the equations, but we're going to go over the 3 forms specifically next. I'm just going to move these things out of the way. And we'll talk about the 3 forms of quadratic equations. So the first form is standard form. And standard form looks like this. Y equals ax squared plus bx plus c. That's standard form. The only thing you care about in standard form really is your c value. It shows you the y-intercept. You can also see the direction of opening, if it opens up or down. And you can also see if it's stretched or compressed in the a value, but that's common for any equation. They all have an a value that shows you the vertical stretch or compression, that shows you the direction of opening. What's special about standard form is the y-intercept, which is the last number at the end. If there's nothing, it's just a 0. So the second form of the equation is factored form. And factored form has a general equation y equals a bracket x minus r x minus s. And in this equation, of course, the a value tells you all the important stuff that a tells you, but the key features are your roots. The r and the s are your x-intercepts, or the roots of the parabola. We have to remember to change the signs. Anything in math tends to be backwards in the bracket, so if there's a minus r, minus s, we have to change the signs for those 2 numbers when we take them out of the bracket. So if it was x minus 2, the root would be positive 2. The last type of equation is vertex form, and the vertex form has a squared bracket and a number at the end. And the important feature in the vertex form is obviously the vertex. The h and the k tell you the vertex. Just like factored form, you have to change the signs for any of the numbers in the brackets, and the vertex is the h comma k. So those are your 3 equations for quadratic functions. Now, we looked at vertex form a lot in chapter 4 because it told us the transformations. So if we just move the other ones out of the way here. Vertex form gives us the transformations of the parabola. So I'm going to include an example. Y equals, let's say, 1/2 x plus 3 squared minus 5. So there's my equation. Each part of this equation tells me where the parabola is located and what it looks like on the graph. So there are certain vocabulary words that we learned in chapter 4. When this value, this number right here, was less than 1, we said it was compressed vertically. And we said it was compressed vertically by a factor of, in this case, 1/2. By a factor of 1/2. The 3 told us the x-coordinate of the vertex. Now we know it's backwards in the bracket, so my vertex is -3, -5. So for my 3, I'm going to say it is translated 3 units to the left. I'm saying left because it's a +3, so it's the opposite direction. And it's also translated 5 units down. Oops. That's my -5 over here. So those are the transformations from this given equation. Now let's bring back our graph that we had here earlier. If we were asked to describe the transformations from this graph, we would just look at where the vertex is located. So it's 1 unit over to the right and 4 units down. And we would look at the first step to see if it was stretched or compressed. We talked about this a little bit earlier. The A value is the first step. It's the vertical step. So it's a 1 in this case. It's not stretched or compressed. So we don't have to say anything if it's not stretched or compressed. It's also not reflected. Reflected means it opens down. So we don't have to say that either. All we would say for this graph is we would say it's translated 1 unit to the right and 4 units down, because it goes over 1 and down 4. So that would be the description for the transformations of this particular graph. Let's add in one more equation where it is stretched vertically and reflected, because we haven't talked about those yet. So y equals -2 bracket x minus 3 squared plus, let's go, plus 4. So the transformations for this parabola, we're going to look at the equation left to right. We're going to do it in order. So the negative sign we'll talk about first, then we'll talk about the 2, then the -3, then the +4. So first of all, the A value is negative. So it is reflected in the x-axis. Sorry for the messy writing here. I'll try my best. Then we have a +2 after our negative sign. We've got a 2. We're looking at these two separate. The negative means it's reflected. The 2 tells us if it's stretched or compressed. That 2 is more than a 1, so it is stretched vertically. Don't forget the vertically, it's important. By a factor of 2. Then we're going to look at the number in the brackets. The opposite of that sign is the x-coordinate of the vertex. So if I were looking to graph this, which we're going to do in a minute, the vertex would be +3, +4. So I'm going to say this graph is translated, which means moved, 3 units to the right and 4 units up, because I'm going 3 units to the right and 4 units up. So if I'm going to draw this on the graph, I'm just going to borrow this grid that I already have on my screen here. Whoops. I'm going to start with the vertex. +3, +4 is up here. Oh, calibration is a little bit off. Then I'm going to use my reflection. It's going to tell me I'm opening down. So the negative sign means I'm going to move over 1 box and I'm going to go down a certain number of boxes. So how many boxes I go down is going to depend on my step pattern. When I'm graphing, I'm going to use the A value, that 2, to figure out my steps. So 1 times A just means 1 times 2 is 2. In this case, it'd be negative, it's going down. 3 times A, 3 times -2 is -6. 5 times A would be -10, etc. We're probably not going to have any space to fit all of those on the graph, but we'll start with the first couple. So here's my vertex. 3, 4. Make sure to label it with its coordinates if you're graphing for me in your exam, please. And we're going to start there. We're going to go over 1 box and we're going to go down by 2 boxes and put our next dot right there at 4, 2. If my screen will let me draw it in there. Let's try. There we go. 4, 2. Then we're going to go over 1 more box right there, and we're going to go down by 6. 1, 2, 3, 4, 5, 6. That's the next point. 5, -4. So we're going to draw in all our points. Then we're going to plot our axis of symmetry. So I'm going to draw a straight line. If I were using my pencil, it would be a dotted line and it would have arrows on either sides. I'm not that good with this app yet, so I'm just drawing a line and I'm going to move it over where it belongs. So here's my vertex. The axis of symmetry goes right through the vertex. And then I can just copy my points over to the other side. So there's one dot and the other one is over here. Happens to be the vertex of the other parabola, but that's okay. So if I'm going to graph, I'm going to draw a nice smooth curve that goes up and comes back down, has arrows, and we're finished. Okay, so that's how you graph a parabola from its equation and how you list the transformations. Determining the equation of a parabola. That is the last thing we learned in chapter 4. So we're going to give an example or two of points on the graph, and we're going to figure its equation algebraically. So I'm just going to move all this stuff off the screen here. To determine the equation algebraically, we're given some information. So we could be given a couple different points. For example, we could say that the vertex of the parabola, is -1, 6, and it passes through the point 3, 2. There's an example. So if we know that the vertex is -1, 6, that's our h and our k in the equation. Another random point is just going to be an x and a y. So whenever we're given points, we ask ourselves, are we going to use factored form or a vertex form? We don't have the roots in this case, so we're going to choose vertex form, which is y equals a bracket x minus h squared plus k. In this particular example, we know that h is -1, so we're going to put x plus 1 in the brackets because we're going to change the signs. The k value is +6. We don't know the a value, and we haven't substituted in our x and our y yet. The x is going to be 3, and the y value is 2. So I plug these two numbers in for x and for y in the equation. Then I'm just going to follow BEDMAS and I'm going to solve. So 3 plus 1 is 4. 4 squared is my bracket. 4 times itself is 16a. And this 6 needs to go over here with the 2. So 2 minus 6 on the other side. 16a is equal to -4. So if I'm dividing both sides by 16, the a value is equal to -4 over 16, which reduces to -1/4. That's the first thing I'm solving for when I'm finding the equation. Then I can just plug it back in. Right, so my final equation would be y equals -1/4, that's my a value that I just figured out, bracket, x plus 1 squared plus 6. In your final equation, my 6 isn't turning out there, but in your final equation, you're just going to use the vertex, but you're going to keep the x's and y's as variables. So this vertex goes back into the equation. I just copied this line because I wrote it out once with the vertex, but without the extra point. And I included my a value back into the final equation. So y equals -1/4 x plus 1 squared plus 6. So now for a second example, let's use a word problem question. We're going to move this out of the way. Let's say that we are kicking a soccer ball into the air. And the soccer ball begins on the ground. So the soccer ball is kicked from the ground. And after 1 second, it's 3 meters high. And it lands at 4 seconds. Let's figure out its equation. So what information do we have? Kicked from the ground means that it starts off at 0, 0. When time is 0, the height is also 0. So that's one of the roots. If it lands at 4 seconds, this is the other x-intercept, 4, 0. So we have both of the roots. Both of these are x-intercepts, which means we're probably going to choose factored form as a method of solving. Then we have a point that says after 1 second, it's 3 meters high. So this point gives us our x and our y. So these are r and s, the 0 and the 4, and the coordinates are x and y. So now we're just going to put those into our equation and we're going to solve. So y equals a bracket x minus r x minus s. My r is 0, so I don't really need to put anything else in that bracket. And my s is 4. So finally, I'm going to put those coordinates in, the 1 and the 3 in for x and y. And I'm going to use BEDMAS to solve. 1 times negative 3 is negative 3a equals 3. So if we divide both sides by negative 3, a equals negative 1. So my final equation then is going to be y equals negative x times x minus 4. I don't really need this first set of brackets there. You can also write it as negative x bracket x minus 4. And that's the equation for the soccer ball. So we've talked about how to recognize it. We've talked about 3 forms of the equation, how to graph, and how to determine the equation. The next thing we're looking at is Chapter 5, which covers expanding and factoring to change from standard form to factored form and backwards. I'm going to do this in a second video so that they're not too big to upload.